Good afternoon, everyone. Thank you, sir. It's nice to speak in a session or program where your teacher is chairing. So Professor Barinde is my direct teacher. So I am proud to be speaking in front of him. So thank you very much, sir. Okay, so in our FDP program, we have designed the program in such a way that in one directions there will be an introductory discussions regarding novel materials, followed by some synthesis route, advantage, disadvantage, etc., and applications. And in another part, there will be a series of lectures on thin films. Okay. So my topic is in the these thin film sections, and today I will speak on Langmuir-Blodgett method, a versatile tool towards molecular electronics. So let's share my hope my slides are visible. Okay, so is it visible?
Yes, sir. Yes, sir.
Okay, thank you. So my topic is Langmuir-Blodgett method, a versatile tool towards molecular electronics. So I have organized the lecture. Initially, I will give a small background of my topic, then some introduction about molecular electronics, and then about Langmuir-Blodgett method, and at the end I will highlight some applications of LV systems towards molecular electronics. Okay, and also I share some future reading for some literature. It's not moving. Please. So please wait. I have some issues on slides. It's not moving. Okay, so now it's working. Sorry. Okay, so whenever we talk about electronic gadgets, you see, always we are interested in devices having increasing computing power, and at the same time we want higher packing density. That means we want to have a device with lower dimensions and increasing storage size. In this regard, co-founder of Intel, Mr. Moody, he gave a famous statement in the year 1965, and he told the number of transistors that can be packed into a given unit space will roughly double every 2 years. That means computing power tends to approximately double every 2 years. You can see in this graph, you see this is a plot of number of transistors in your CPU with year of evolution of the corresponding chip, and you see it's almost linear. And now we are here in your chip. We may have roughly say 5 into 10 to the power 10 number of transistors. You see. And in this cartoon, I am showing just a pictorial idea. You see the size of an almost oldest computing machine, ENIAC, in 1947, almost equal to a big hall. And now you can see 1 million number of transistors you can pack in a finger tip. At the same time, if you look here, say a small SD card in the year 2005, you can see the size is of the order of 120 MB. But now you can see it's in 2004, same size, but the storage capacity is 128 GB. Now you can have TB order also. Here you can see the size of your processor. Here it's very big, but here very small in size. Okay. So everything was going good. In 2012-13, that time, the individual feature size reached of the order of say 25 nanometer. And then Moore gave one statement. I see Moore's law dying here in the next decade or so. Why he said? Because he thought scientist has achieved the lower dimension size of the devices, and maybe it might not possible to go further lower dimensions. At the same time, the CEO of Intel, Mr. Brian, he commented that in his work period, in the last 34 years, he has witnessed several times people raise doubt about Moore's law. That means how further we can go at lower dimensions. At the same time, he said, every time I have seen Moore's law is going ahead, it's still alive. How this is possible? Why this is possible? This is because the development of material science, especially nanotechnology and molecular electronics. Here in this graph, you can see the size of your device with the time. In school or lower classes, we have read about vacuum tubes. That time, vacuum tubes was the diode, triode, etc., transistor bulb, and it was vacuum electronics. And this kind of systems was the basic building blocks of the electronics, and the size of the devices was of the order of meter. But now, with time, with the invent of semiconductor, we attain solid state electronics. At the same time, size decreases enormously. And in this way, we reached microelectronics. Now we are using VLSI technique, very large scale integration, and feature size of the order of micrometer. Now scientists are aiming to have molecular electronics, where individual molecule or a group of molecules can be used as a basic building blocks of the electronics devices. Now, what is molecular electronics? Molecular scale electronics is a branch of nanotechnology where we use single molecules or nanoscale collections of single molecules as electronic basic components. It is an interdisciplinary area that spans physics, chemistry, material science, almost all areas of science subjects. The main goal is to shrink the electrical circuit, that is lower the dimension, and at the same time increase the efficiency as well as speed. And it provides a potential means to extend Moore's law beyond the foreseen limits of small scale conventional silicon integrated circuit, because with silicon using as the basic building blocks, there is a limitation of size shrinkage, and almost we have reached at the limit. So to keep the Moore's law alive, scientists are trying nanotechnology or molecular electronics can remain the law valid. In here I show some examples where individual molecules or a group of molecules are used to represent some devices, say molecular rectifiers, molecular wires, molecular switches, molecular sensors, molecular transistors, etc. These are already, there are so many reports Therefore, if we have to realize molecular electronics, it is important to organize, as at the same time manipulate the materials at molecular level, so that we can play with the material organization to have some specific desired properties. Langmuir-Blodgett films or Langmuir-Blodgett technique can play a vital role in this regard. This is an important thin film preparation techniques, especially one can organize molecules at nanoscale dimensions with molecular level control over the layer using this technique. Here I show an image taken from Wikipedia. He is Mr. Mark Retnard, and he did lot of works in molecular electronics. Especially he designed unimolecular rectifier, and he mainly used the Langmuir-Blodgett technique to align or organize molecules in single molecule layer. And he is known as the father of molecular scale electronics. And you can see he has received so many awards, and out of this one is Irving Langmuir Award, and which is this Langmuir is the pioneer of this Langmuir-Blodgett technique. Now, LB technique is a thin film formation techniques. So what is a thin films? You can see in this cartoon color in the wall, or maybe in rods, or putting in the card window. All these kind of materials are some kind of putting. Okay, but in electronics we are interested in thin films which is much lower in dimension, much lower in thickness, of the order of nano to micro level. This kind of thin films are important two-dimensional nanostructures, and already Professor Minal has shown this thing, confinement and in dimensions. If you want to have your system in nano dimensions, normally in physical observables, all physical observables have 3 dimensions: length, width, and breadth. If you want to your system to be under nano, then at least 1 dimension had to be confined, cut down to the nano dimensions. If you cut 1 dimension, then you will have a thin films. This is called 2D structures. If you cut 2 dimensions, you will have 1-dimensional structures, some kind of nano wires, quantum wires, nano rod, etc. If you cut all the 3 dimensions, you will have 0-dimensional nanostructures, quantum dots, nanoparticle, etc. So here the Langmuir-Blodgett films is a 2-dimensional nanostructures. And this is of course already discussed by a previous speaker. This LB technique is a bottom-up approach, where we will assemble or assign or organize molecule by molecule to have the desired structures. Okay, so this is a bottom-up approach. How thick this kind of thin film is? Thickness of this Langmuir-Blodgett films or thin films in such that the properties of the materials are affected. There are so many discussions in earlier talk also. A main beauty of nano is that if you achieve nano dimensions for any material, you will have new properties. Almost all kind of properties, optical, electrical, thermal, even mechanical, everything you will have new properties. Okay, so here thickness should be in such a way that your property of your material is affected. Typically, the thickness is of the order of nano to micrometer order.
So when I go to
the importance of such thin films is that these thin films are found promising in many practical and commercial applications, like almost all kind of displays, because display is a vital part of your electronic gadgets, starting mobile, computer, everywhere you need display. So display is some kind of coating of thin films, then detectors, sensors, electronic circuit components, and so on. Now, we already know that thin films has very low dimensions, nano to micro, and in nano to micro, we cannot see it with naked eye, we cannot hold it with our bare hands. So due to smallness of small thickness of this kind of materials, you need special techniques to prepare, to handle, to organize this kind of materials. Okay, there are several techniques by which you can prepare this kind of thin films or organize. You can organize materials in thin films, such as say spin coating, adsorption from solution, lithography, electrodepositions, LV technique, self-assembly, sputtering, thermal evaporations, and so on. So here I will discuss about Langmuir-Blodgett technique. Why the study of LV technique is important? This is because this is an unique blend of physics, chemistry, and molecular engineering. You can have idea about physics, chemistry, as well as engineering of your systems by using these techniques. You can have idea about the structure property relations, how the organization of your molecules change or affects the property. Then you can have homogeneous depositions of large area of the order of monolayer or maybe double layer, triple layer, like this kind of organizations. You can have multi-layer structures with varying layer compositions. That means you can use more than one molecule, one layer, then another molecule, another layer. In this way, you can have your desired structures. And this way you can have two-dimensional structure. At the same time, you can have three-dimensional structure also. And main important thing is that the techniques give you an intrinsic control over the organizations of your material. And that means control over the properties of your materials organized in thin films. And you can organize your materials almost in any substrates using these techniques. So these are some importance. And people are doing studying physics and chemistry of the complex systems at lower dimensions, then deposition of different kinds of monolayer on top of each other to create desired physical phenomena or device, study of mixed molecular monolayer and self-aggregation, and then two-dimensional aggregations, fabricate some biomolecule lipid kind of layer, because LV technique is very important to have to mimic biomembrane artificially. One can prepare artificial biomembrane and can study the properties to have the property of the biological system in an artificial way. A lot of applications are proposed, say organic LED, then ICs, solar, then mimicking biological systems, sensors, memory chip, nonlinear optical effects, switching, then electrical circuit components. So many applications are coming up. Okay, so let's see some historical perspective of the LV systems. Long back, this man, Professor Benjamin Franklin, reported the experiments where he sprayed oil on the water surface, and he demonstrated that this oil film spread almost uniformly on the water surface. And this was the say beginning of the idea of LV systems. Then in Auguast, she demonstrated that this oil layer on water interface can be controlled by movable barrier. Then Lord Rayleigh, he demonstrated that the thickness of such layer is 1 molecule thick. Later, Irving Langmuir demonstrated that this monolayer can be systematically transferred from air-water interface to solid substrate. And for this work, he awarded Nobel Prize in 1935. Then his student, Catherine Blodgett, demonstrated that one can systematically deposit this layer to have mono to multi-layer. That means desired thickness in solid substrate. And from this name of these two scientists, the name Langmuir-Blodgett was given as a whole for the techniques. These are some instruments. You can see the LV instruments. These are now very modern systems with computer control. One can prepare the layer in water surface here, then one can deposit. Okay. Okay, so we will discuss step by step. Okay, so there are two steps for LV technique. One is one has to prepare the molecular layer in the water surface. This is known as Langmuir monolayer. Then one has to deposit this floating layer onto solid support, and this is known as Langmuir-Blodgett films. And this is ready for your characterizations or further use in devices. Okay. So normally for LV technique, one has to use the material which will ideally float in the water surface. And this kind of material are known as amphilic molecules, and this will have one hydrophobic part and another hydrophilic. Hydrophobic part will not interact with the water. Hydrophilic part will interact with the water. For example, say stearic acid. The COO bond, they will interact in the form of, say, hydrogen bonding with water, and the long chain will remain at the upward direction. So as a whole, this material will float in the water surface. So these are ideal. But of course, water soluble material can also be used in LV technique. Okay. So solvents, first you have to prepare solution of your materials using water insoluble volatile solvents, say chloroform, benzene, etc. Because you will prepare solution of your materials in the solvents, then you will put the solution in the water surface. If your solvent is water soluble, then your solution at the same time molecule also dissolve in water. That's why you need water insoluble solvents. Then you have to be very careful because you are dealing with a monomolecular layer. So your LV trough, that means where you are spreading your material in the water surface, should be very clean. Then your surface also should be very clean, and normally people use water, mercury, glycerol, etc. for surface, and commonly or most popularly water is used. Okay, then you prepare your solution in water insoluble solvent, then you spread your known quantity of your solution in the trough. You can see this is the trough here with a micro syringe very close to water. Then your material will remain on the surface, and your solvent is water insoluble and at the same time volatile. So if you wait sometimes, your solvent will evaporate and only your molecule will remain in the water surface. They will float. Okay. So since you are working with the surface, so surface tension is very important in this regard. And we all know this thing that in the within the surface, the cohesive force among the molecules balance each other, because in all directions they exert at same force, so they will balance and cancel out. However, in the surface you can see there is an imbalance, and they will feel extra tension towards downwards, and this will lead some extra free energy on the surface. And this is vital here also, because we are spreading the molecule on the surface, so we have to take care of this issue. Okay. So in LV systems, there is a term we say surface pressure. Normally, surface tension of pure water is of the order of 70 to 72 millinewton per meter. When we add impurity on the surface, then surface tension decreases. So in LV system, we put material in form of solution in the surface. That means surface tension decreases. Then we measure the surface tension before putting the solution. That means for clean surface, then after putting the solutions, and we take account the difference of these two, and this is known as the surface pressure. Okay, and you know, depending on the number of molecule on the surface, this value changes. So if one can have idea about the number of molecules and the total area, that is area per molecule, and can measure this change in surface pressure, then one can have idea about the organizations or interaction about the systems. So in LBC systems, we measure these things. Okay, so this is done using Wilhelmy arrangement. Here, a plate is dipped on the surface. You can see here, and if one knows the dimension of the plate, then one can have idea about the force, because one can measure the weight, then buoyancy, then surface tensions, and from this one can have idea about the resultant force acting on the plate. Okay, so in initially we spread the molecule in the surface, and the barrier, that means this barrier is kept in a expanded position. That means area per molecule is very large, and molecule remains separated from each other. They are free from each other. Interaction is very less, and this is comparable with gas phase. When we, and you can see here, in that case the surface pressure is very less, area is very high. Now if you compress the barrier further, that means decrease the area per molecule. Molecules come closer, they start interacting, and we say that this is close to liquid phase of the systems. You can see here, this is shown here. Then when the molecules touches each other, we say that this is solid phase, and in this phase you can see that pressure is increasing very high, but area is almost same. It's like solid. If you apply force, you see your dimension or size, shape is not changing, but force is increasing. Okay, but after some force, your solid will collapse. Here also same thing happen. If you go on increasing or the applied force, you see the layer is collapsed, and in that case you see the plot, you see here decrease in surface pressure. Okay, this is here again shown. Depending on the molecules and organization, one can has different kind of phase. Okay, so this is an indirect way of having idea about the molecular layer at air-water interface. From this, one can have idea how molecules organizes in the surface at air-water interface. Okay, so this is a floating layer in solid phase, that is molecule close to each other. Then this is after collapse, so many things may occur, maybe aggregation, maybe double layer, so many issues are there. So one can study this kind of things. Factors governing the monolayer phase behavior, because these are in molecular level interactions, so there may be van der Waals interactions, short range forces proportional to the power of r⁻⁻⁶. Then ion-ion interactions may be due to charge of the materials, electrostatic interaction there, dipole-dipole interaction may be there. Then of course pH, temperature of the surface, that is water, may also play the interactions or monolayer phase of your floating layer. Once you have your floating layer ready, then it is ready for deposition, that is transfer onto solid substrate. So one can use any kind of substrate starting from glass, alumina, tin, silicon wafer, silver, almost any kind of solid support can be used based on your applications. For example, if you want to do some kind of electrical characterization, one can use ITO coated glass. If you want to have say FM or SEM studies, then you need some smooth, maybe silicon wafer or maybe cover sleeve, this kind of things. Okay. Then depositions, there are some deposition schemes. These are Y, X, and Z. But these are very simple. How we do it? Normally, we spread the material, we make the material come close to each other to form the floating solid layer. Okay. Then we dip a substrate just in between the floating layer and take out. Okay. You can see here. Then the molecule attached with the substrate. Again, if you dip, you can transfer, you see the second layer. In this way, by repeating the dipping and taking out the substrates through the floating layer, one can have multi-layer depositions. And depending on the deposition, that means interactions of your material in multi-layer, these name X, Y, and Z. You can see here, if this is your tail part, that is hydrophilic part, this is your hydrophobic. And this is hydrophobic part of your second layer. So if the interaction is similar, that is hydrophobic, hydrophobic, hydrophilic, hydrophilic, then we say this is Y type. Then again, here you can see this is interaction is hydrophobic, hydrophilic, hydrophobic, hydrophilic, then we say X type. And if it is hydrophilic, hydrophobic, then we say Z type. And of course, depending on these organizations, the property of the material changes. So this is important. One can have superlatives, that means heterostructure also. That means different kind of material one can prepare in this way. Okay. So this is again, okay. So, and there is another way of transferring this floating layer. This is known as Shaffer method or horizontal technique. Here, horizontally, you can just take a solid substrate, maybe a glass substrate, very close to the floating layer. Gently you touch and you see that your material will attach here. But of course, the whole system is computer controlled, because if you want to have it physically with your bare hands, a minute jerk can change the organizations. Okay, so this is horizontal. So all this kind of deposition is very important, because organizations or arrangement of your molecules are different. So this LB techniques give you a variety of options to organize your material in a desired way. Okay, so once your material is transferred, you can have idea how many floating layer, how much extent is transferred onto your substrate. How? Just by you record the area of the floating layer before and after deposition, and you measure the area on the substrate covered by the film. And if you take a ratio, this is known as transfer ratio. If it is 1, that means decrease in the floating layer area, and putted area in the surface is same. That is a very good. Okay, but of course it's not always same, because so many issues are there. Okay, so here a small animation, you can have idea about the whole process. You can see here, this is the LB trough. We deposit the solutions. You see the solvent evaporate, the molecule remains on the surface. Now we compress the barrier. You see the pressure is increasing here. Molecules is coming close to each other. Then you take out your substrate through the layer. You can see the floating layer attached with the substrates. Then you take out and you apply your material in the for characterizations or applications. It's very easy to understand. Say we all know this kind of planes, water planes floating in the ponds or lakes. If with a bamboo stick you start compressing or accumulating the floating planes side by side, you will see area is decreasing, planes is coming close to each other. Same thing happen here. And there will be a situation when planes will touch each other. That means a solid layer is formed. If you further compress, then your planes will slide upon each other, or some will cross the bamboo, that means collapse. And once your floating layer is ready, then we have to transfer, and we can compare it like that. We all know when we heat milk, there is a creamy layer formed. Okay, so if you dip a spoon upon the floating cream and take out, you will see that cream will attach with the spoon. So same process here. Okay, so it's very easy to say, but difficult to realize, because you cannot see it. It's molecular dimension. So there are so many ifs and buts. You have to optimize everything. You have to be very careful, because a minute flow of air or dust may affect everything. Okay. So as a whole, LB technique has two parts. One is preparation of floating layer at air water interface. This is known as Langmuir film. Then transfer of your floating layer onto solid substrate. This is known as Langmuir-Blodgett films. Once your film is deposited, then you can characterize it. There are so many techniques. During preparations, we study pressure area isotherm. I already told you this is a measure of area per molecule with change in surface tensions of the floating layer or maybe interface, air-water interface, when you spread your material. From this, you can have idea about the organizations of material. This is one can say that this is a fingerprint kind of things, indirect way of having idea about your floating film organizations. You can do other studies like say Brewster angle microscopy, fluorescence imaging microscopy, to have idea about the structure of the floating layer. Then you transfer your material into solid support. Then you can do lot of characterizations, say spectroscopy. You can do absorption. You can do fluorescence. You can do FTIR, NMR, Raman, etc. Depending upon your applications or what kind of characterization you want to do or what kind of property you want to explore. You optimize your characterization techniques. You can do XRD also to have idea about the structure of your layer. Then you can do microscopy. There are a lot of microscopies, but of course optical microscopy is not working because this is nano dimensions, and with optical microscopy it's difficult to go beyond say 200 nanometers. There are certain limits, so we use AFM, atomic force microscopy, scanning electron microscopy, transmission electron microscopy, and there are other systems also. Okay, and during the preparations of your LB films, one can play with some parameters. Say one can change the pH of the surface, then temperature of the surface, then one can spread a mixture of the systems, then one can deposit the material changing various pressure and also various number of layers. So in this way, as a whole, LB techniques give you a number of parameters or options by playing which you can play with the material organizations and hence the properties of the materials. Okay. So now I am sharing some examples where LB films or LB technique have been used to to assemble or organize materials at molecular level, having some specific applications. So this is a work we have done in our lab where we have prepared some organic nanowire as well as nanorod with a imidazole derivative. It's an organic material prepared by one of my collaborators in chemistry, and we have prepared this material using LV technique. Okay, and you can see this is a nanowire of this material having say thickness of the order of 100 of nanometer, and then maybe height less than 6 nanometer. Similarly, nanorod, you can see height of the order of 20 nanometer, and then diameter may be close to 200, more than 200 nanometer. Okay. And the main issue is we tried with other techniques, say spin coating technique, then cast film also, and layer by layer deposition also. But in all these techniques except LB technique, we didn't find any this kind of nanostructure formation, nanowire or nanorod. And this is mainly because in LV technique, when we spread the material at the water surface, they form hydrogen bonding and they form a number of say molecules close to each other through hydrogen bonding and form a molecular wire kind of thing having two molecules side by side. Then this molecule form J aggregates. Okay, and in J aggregates, molecule forms stacking, head to tail arrangement, and we have shown here it's a stacking of molecules of hydrogen bonded molecules. Okay, and they form a big floating layer kind of thing. Then in LV technique, we can compress the layer using the barrier. So when we compress using the barrier, this layer fold. You can see here schematically we have shown it's folded and form nanorod kind of thing. And by manipulating the speed of this compression as well as depositions of the floating layer onto solid substrates, it's possible to have different size nanorod or nanowire kind of structures. This is interesting. Okay, and then we studied the electrical behavior of these systems, organized material, and here we have shown, you can see, when we prepare using cast film or spin coating, it's, you see, ohmic behavior, almost linear voltage and current. Okay, but when we prepare this kind of nanostructure using LV technique, you can see it shows electrical switching behavior. This is similar to threshold switching, resistive switching, and it can have memory applications. So here we can say that this LV technique play a vital role towards preparation of this kind of organized nanowire nanostructure, which is difficult or almost impossible to prepare using other techniques. And here mainly charge transfer between donor and acceptor group was the key towards this kind of electrical switching. So we propose it can be used for memory devices in future. Then I am showing another example where we used a phenazine derivative. This is again another organic material and synthesized by one of my collaborators from Calcutta University. And we again designed some kind of memory devices. It's a crossbar kind of devices. Here you can see this is this white part. This is LV layer of this phenazine. And these are electrode, gold electrodes. We have put it using lithography. It's a crossbar device like this. And this LV film, we use a mixture of this phenazine and stearic acid. An interesting thing is that we have observed that by controlling the mixture or mixture ratio, it's possible to have ROM kind of behavior as well as RAM kind of behavior just by changing the composition or ratio of mixing of this phenazine and stearic acid. And we propose it, the ROM can be write once, read many, and another is resistive random access memory. So here you can see that here we have assembled the phenazine and stearic acid with a composition ratio 1:3 mixing ratio. And here we have seen that the device shows WORM, that means write once, read many types of property, and it's can be used for organic ROM application in future. And here you can see when we change the compositions, phenazine SA at 3:1, just we opposite the ratio, you can see they showed RAM behavior. Okay, or this title is wrong, sorry, it's RAM. You can see when we apply voltage, at certain voltage is go to the low resistance state. Then again, when we go on opposite scanning, it again come back to its initial high resistance states. So it's reversible. It's RAM kind of behavior. Okay. Then we studied the retention characteristics, and we have seen that once the data written, that means the state of the device is changed from one state to another, it can hold up to say 150 hours, okay, without changing the resistance of these states. And the difference between high state and low state is of the order of greater than 10 to the power 4. That is memory window is very high. So this kind of material can be a very high potential towards realizing molecular electronics memory devices in near future. Okay, and here our main system is mainly some conformational change of the material occurred, and in 1:3 composition, if you image is not here, in AFM we have seen that some porous kind of structure is created, and that means some kind of traps is there. So once biasing is there, so charge or electron is trapped within the trap permanently. So even when biasing is stopped, still it can hold its low energy state. That is, it remain in high state. So next time when you apply the bias, we can see that already the system is in low resistance stage. So it works as a permanent memory kind of thing. Then I am showing say another structure. This is a biodegradable memory using protein, and here we have seen that this memory is a shows ROM kind of behavior. Once we apply bias, our resistance of the system changes from high resistance to low resistance, but it cannot come back to its high resistance state even when we remove the bias. So its change in resistance is permanent in nature. And interesting thing is that we have seen that once the state of the device is in low state, it can retain its low state up to 10 years. We studied it up to 10 to the power 6 seconds. That is almost, say, close to 1000 hours experimentally. Okay. Then we applied some kind of extrapolation, and we have seen that almost 10 years it can retain the stored information, and which is a very good period to have real practical application of such systems. Then we studied the read endurance. That is, once we change the state of the device from high resistance to low resistance, then we go on reading with some intervals of the order of, say, a fraction of seconds, and we can see that almost, say, 36,000 times we can read the stored information. So, and the memory window, say, of the order of greater than 10 to the power 3. That means difference between high state and low state. Then read endurance, that means number of times we can read, is greater than 3.6 into 10 to the power 4. And also device was stable for more than 210 days. And even after 210 days, we found it stable. But maybe it will have more stability if one go on studying. But in lab it's difficult. So we stop characterizing beyond 210 days. And device yield means you will prepare a number of device, then you will compare how many devices show memory behavior and how many is not showing. That means probability of your having switching behavior with respect to total number of prepared device. And we have seen that device yield is greater than 87.5%. So this is also very good. And data retentions experimentally, data can retain greater than 10 to the power 6 seconds, and extrapolation show that this kind of memory can have lifetime more than 10 years. So as a whole, this is a very promising material organized using LV technique for future biodegradable memory. And another thing is that this kind of system is transient in nature. Transient electronics, where you will prepare devices for your electronic circuit components, and you will go on using this. Once your application is over, what you will do, you will say dissolve your circuit in some kind of environment friendly solution, maybe water or some kind of other solvents. So here we have seen that our device can dissolve totally in water in 8 minutes. So this is a very good promising material for transient electronics also. And this kind of system has a lot of applications in biomedical device, because you can if you can implant biomedical device using this kind of material in say body or other inside the body, and say after using or once the application is over, it can dissolve or it can the circuit can exhaust or without needing further removal of the system from the body. So transient biodegradable transient systems is a very promising for future transient electronics, biodegradable electronics also, because nowadays uses of data is increasing. Everyone is using say internet, memory of the order of giga order every day. So in near future, Auguast is a tremendous problem people will face in near future. So in this respect also, biodegradable memory can be a good solutions where your material is biodegradable and will lead very less environmental problems. So this work is under communications. Then for future reading, if any of you are interested in Langmuir-Blodgett techniques, so you can, I have shared some review article. There are so many review articles there in the internet, but here I have shared 3, one from our group in Helion, then another from Ariga group, one is Advanced Matter, another is Langmuir. So if any one of you interested, then you can read, and at the same time you can say visit our website also to have our works, because this lecture is a introductory kind of thing, basics of the thin film preparation techniques using Langmuir-Blodgett method. So we didn't go elaborate or deep into say any results, just an introductory idea. So if any of you interested, you can go through our publications, you can interact by email or here also. Okay, so this is some acknowledgements with my co-workers, students and colleagues and collaborators, then funding agency as a whole. So I am grateful to them. So thank you for your patience and listening. So now if you have any questions, you can ask.
Thank you, Dr. Hussain, for the deliberation of the lecture to the faculties who are eager for some days to listen this. And now I shall request the participant to put their queries to the chat box, and we shall place it to the Dr. Hussain, who will be giving response to your queries one by one sequentially. So please put it to chat box without going to audio method.
Okay. So very interesting. Okay. Can organic solvents used for LB thin films formations have both higher and lower densities than water? Okay. So organic solvents is possible. Okay. Normally we use organic solvents for solutions. In LB techniques, you have to prepare your material in solutions. Then you have to spread at some interface, liquid air interface. So normally we use water, but you can use other liquid also. Okay. So, but remember, the surface tension should be very high because when you put your material in the surface, your surface tension is changing. So you can have idea, you are recording this thing. So water is used as the surface. This is very common. But any solvent you can use for preparing of solutions. But it should not be water soluble or the liquid you are using in the trough. If it is your solvent is soluble in the trough liquid, then your molecule will go down. Not remain in the surface. Because our aim is to organize the material on the surface, then we will compress, then we will transfer. Okay, so in this way you have to optimize your solvent for solutions and at the same time liquid for your LV trough. Then can any polymer composites be deposited on semiconductor? Yes, in principle, any material you can prepare. But logically, since you are making your layer initially on the surface, that means it will float on some liquid surface. So you have to choose your material as well as liquid in such a way that your material should not go down to the surface. That means it should not dissolve in the liquid of the surface. Okay, so this is important. But even if it is soluble, still you can prepare. In this regard, you have to take the help of other matrix molecule. Matrix molecule in the sense, say, if you want to study the electrical property of your material, which is water soluble, then what you can do, you can take help of other material, which is electrically inert, and at the same time remain at the water interface. So this kind of material can help you to take your material at the surface. So it's possible. So you have to optimize the system. What is the minimum thin film trough LV technique? What is the minimum thin film throw LV technique? Okay. So minimum means, I think you asked minimum thickness. In principle, ideally, it's possible to have thickness of the order of 1 molecule thick, because you are putting your molecule on the surface and they will float one molecule one by one. Okay, just like say a water plant or something like that. Then you will compress them side by side, then you deposit. So ideally, it's possible to organize a film at 1 molecule thick, but practically it's sometimes difficult because its molecular level dimensions, if you transfer, there are so many issues. One issue is at nanoscale or molecular level, materials self-assemble, because there are so many forces, maybe capillary, van der Waals, electrostatics, hardly you can control. How you will control? By changing the environment. Okay, so there are so many issues. So you have to play with the systems, and if you can optimize in a suitable way, in principle, you can have 1 molecule thick layer. Can there be any issue of adhesion of thin film in onto the substrate? Yes, this is important because you have to optimize the substrate also, because substrate property is vital. Okay, for example, if you use say hydrophobic substrate, then it will interact with the hydrophobic tail part of your material. If you use hydrophilic, then it will interact with the hydrophilic part if you deposit in Y type. So in this way, interaction between substrate molecule and your material is playing some important role. Okay, so you have to play with these things. You have to optimize the substrate as well as materials to have some specific property, adhesion, and at the same time cohesion also, because interaction between molecules of your material is also vital during organization. So you have to play with the things. Okay. What is nonlinear optical lithography and Wilhelmy plate? Okay, so lithography, actually lithography, we didn't do lithography. Okay, so normally, for example, I have used lithography. Actually, they used some kind of electron beam to organize the material on this surface or change the property. Okay, so we didn't do it here because in my lab we are not doing. We have deposited the electrode using lithography on the material from IIT Mumbai. They have this Indian Nano technology user program or something like that. So they did it for us. Okay. Wilhelmy plate. What is Wilhelmy plate? This is a simple plate. You can use say a copper plate or a filter paper like this because Wilhelmy system is mainly a technique to measure the surface tension. So anything you can use, a simple paper. If you want to know the dimensions, you dip into the surface and across the material, and it will be connected with a balance. So you will measure the weight before and after the material is connected with this, and then you can have idea about the surface tension. So as a plate, you can use anything, a paper or copper, whatever may be. In our system, we use a blotting paper. How are the heterostructures patterned in LB? Okay, so heterostructure means say in LB technique you can organize your material in a molecular layer. So you want to organize a heterostructure using two different molecules. Okay, so how you can do it? You can prepare a layer of A molecule first, then layer of B molecule, then again layer of A molecule. In this way, you can do alternately. Again, you can do say in the same layer, you can during spreading, you can mix two different molecules. In that case, your material will organize in a heterostructure in this same layer. Okay, so in this way, by playing with the systems, you can have a heterostructure of monolayer having composition more than one material, or multi-layer having alternate of different material, 2 material, 3 material, 4 material in this way, and then you can study your property. It's possible. Yes, non-ohmic behavior, yeah, because you know I have shown the switching behavior. These are non-ohmic behavior. This is not linear, so it's possible. This it depends because you know I have shown but shared this resistive switching, and this is for organic material, and there are you know so many mechanisms proposed for this. So, for example, say maybe if your material have donor acceptor systems, then maybe charge transfer from donor to acceptor may be an important issue. There may be change in organization of functional group, that is conformational change of your molecule. There may be traps, there may be oxidation reduction process, etc. So many issues are there. So your LB technique can give a favorable process for this kind of switching, that means nonlinear behavior in electrical characterization. So it's possible. We have already designed some switching material having nonlinear behavior electrically. Can we measure IB characteristics of a semiconducting material in its solution form? Solution form, I think it's possible, but in that case, your solvent is also important, but we didn't do any characterizations in solution form. But I think it's possible. But you have to, in that case, you have to optimize your measuring environment, because in solution material is moving, you know, floating, and maybe distantly, you know, placed. So sometimes may be difficult, but I don't know exactly because we didn't measure any IB characteristics in solutions also. But of course, solvent will also play some important role. Conductivity of the solvent also.
বাপ্পাদা বলছে যে তুই যে ডাক্তারকে দেখাইছিস তার কনসাল্টে চল ক্লিয়ার আছে তো সেটা বলছে সেই কারণে
Participant may put more questions. I think 2 or 3 more questions. If you desire, Dr. Hussain will be pleased to answer more questions because we are having some time for this session.
এমনিতেও বললো না
সেটা বলে ওই জিনিসটা বলবো
Okay. Okay. I am available throughout the program. So for any information, you can contact with me through WhatsApp or email. So sir, please.
Thank you, Dr. Ashad Hussain, for giving nice lecture in relation to LV technique. In fact, before starting the lecture at the beginning,
থাকে
he has given a good introduction to the importance of molecular electronics with respect to molecular memory device. Thereafter, he has marked one thing. After 2012 and 2013, how the scenario changed. It's an interesting history. Then he go into the actual topic, LV method. LV explained very nicely. Several examples given. In terms of photography, very good. So I think all the participants are within their expectation and have enjoyed nicely the lecture, which I have also enjoyed nicely. So as Dr. Asha told, he will be available around 3 or 4 days. This conference. You can make contact with him via WhatsApp or any other media as available. So thanks to the participants for their patience hearing, and I also thank to Dr. A. Hussain for delivering such a good topic and nicely in front of the, I think there are a lot of new generation in this field attending the lecture, and it will be very much, and I would request the participant to go through the review articles as told by Dr. Asha at the end of his lecture. These review articles will help them very nicely. Okay, thanks to all. Thanks to Dr. Asha. Okay.
Thank you, sir, for chairing and helping to organize the first day program. So thank you, sir. And I also thank all the participants. So today we will stop here. Tomorrow we shall start sharply at 10:30. I request all the participants to join online by 10:15 a.m. 10:15 a.m. So till then, goodbye. Take care.